Hello everyone, myself Dr. M. Karunakar from Eving Christian College, Allahabad, UP, faculty member in the Department of Chemistry. Today I want to introduce the topic organometallic compound. What are these organometallic compounds? Definition: these compounds contain carbon-metal bonds, or metal is directly bonded with the carbon atom. You can see carbon is directly attached with the M. Yeah, alkyl group is directly attached to the M. So what is the nature of this carbon-metal bond? Is this ionic or covalent? So it depends on the presence of the metal atom. So we can see in this list sodium, lithium, magnesium, aluminum, zinc and lead to mercury. They are bonded with the carbon atom and it is showing the percentage of ionic. Suppose when we see in this carbon and sodium, it is 65% ionic and lithium is 60 and magnesium is 52%. So this ionic characters actually basically depends on electropositive character of metal. What is electropositive? Electropositivity of the element is losing tendency of electron. So those elements, their tendency to lose their electron so that they become easily positive. So those more electropositive elements they are in more ionic character. So here we can see from this table we can conclude here carbon sodium, carbon lithium bonds are highly ionic compared to carbon magnesium, carbon zinc and carbon copper. Right. So based on this we can propose the reactivity order of main organometallic compounds. You can see here organolithium is very powerful reactivity. Thereafter organomagnesium, then organozinc. So organolithium compounds are alkyl lithium and organomagnesium compound example RMgX, alkyl magnesium halide, and organozinc compounds we can give example the stable reagent dialkyl zinc. So what are the applications of these organometallic reagents? So these reagents actually useful for the many new organic synthesize many new organic compounds. They are also useful for the new CC bond formation and they are very good source of nucleophile and base. So we will discuss today Grignard reagent, that is organomagnesium reagent. Look at in this slide the preparation of Grignard reagent, that is alkyl magnesium halide RMgX. The starting materials are alkyl halide in the presence of magnesium metal, in the presence of solvent ether, it will give this reagent. So here the examples are given for the alkyl halide. The alkyl halide, they can be 1 degree, 2 degree, 3 degree. Yeah, alkynyl halide, yeah, alkyl halide or aryl halides. X also chlorine, bromine, iodine. Chlorine is not taken here because of the highly reactivity of the chlorine. And the ethers example diethyl ether and cyclic ether, that is tetrahydrofuran. So the order of the reactivity of alkyl halide is alkyl iodide, then alkyl bromide, then alkyl chloride. So these are the some of the example where we can see the preparation of various different type of Grignard reagents. So what is the role of these ethers? So these ethers basically they stabilize the Grignard by through their non-bonding electrons. You can see in this picture at bottom. That's why ethers are obligatory solvent for the Grignard reaction. So this reaction doesn't work without these ether solvents. So what will happen if we are not using ether? The magnesium will be oxidized and become magnesium oxide. So even though sometime if Grignard is not stabilized by ether, they can react with the atmospheric oxygen to form peroxide, and with the carbon dioxide they can react with carbon dioxide to form acid. So this is the general mechanism have been shown in this slide. So magnesium in valency shell, it is having 2 electrons are available, and the homolysis of these alkyl halide provide this radical, and this alkyl radical combined with this magnesium one of the electron to form MgX radical. Later on recombination of this R radical with MgX. So there are certain limitations because all kind of alkyl halide cannot provide or synthesize these Grignards because they are not stable after the reaction. So we can see some of the limitations of this Grignard. In the first case, the benzyl halide and allyl halide do not give stable Grignard. How? We can see here benzyl halide with magnesium in presence of ether, it is formed Grignard over here, but this is not stable. It is further reacted with its original molecule undergoing substitution reaction because this is CH2 minus and MgX plus. This CH2 minus substituting on this CH2X position, CH2 position, so the X will be eliminated. So you are getting this dibenzyl product. That's why benzyl halides are not give stable Grignard. Even the same allyl halide also the same pattern we can see over here. The second limitation is if the alkyl halide having any acidic functional group, then also the stable Grignard will not form, but it will further react to form with the acidic hydrogen give different product. Look at here, this the alkox alpha gamma hydroxy alkyl halide I have taken here for example. So here initially Grignard will form. As I told you, this R part, R minus, act as a base based on the condition. Here acidic proton is available, so that's why abstracting this acidic proton from its original molecule, this Grignard abstracting this OH proton so that it is giving alcohol as a product. That's the reason acidic hydrogens, if they are present with the alkyl halide, they also do not give stable Grignard. And the third one, you can see the 1,2 diols. You can see they were also undergoing dehalogenation to give alkene instead of Grignard. So here I explained here, suppose one of the halogen atom is reacting with the magnesium in presence of ether, it may form like this Grignard. After that, this this R minus act as the nucleophile. So this is through this bond undergoing elimination, it is giving alkene as a product. Similarly, you can see in the 1,2-dibromobenzene, one of the bromine involved in Grignard formation, thereafter undergoing elimination, you get here triple bond, that is the benzene. Here it is double bond. After the elimination, this carbon-carbon bond is triple bond, that is benzene. This is benzene intermediate, further dimerize, it will give this product. What about 1,3-dihaloalkane? It is a Frand reaction in presence of magnesium. Here 1,3-dihalo compound in the presence of magnesium. It is giving cyclic compound, cyclopropane product. Here it is formed instead of Grignard. So it is clear that 1,2-dihalo, 1,3-dihalo compounds, they do not give Grignard. As I told, Grignard, where R part nucleophiles, they can act as a nucleophile, also act as a base based on the condition. They abstract the acidic proton and give hydrocarbons. Here I have given the list of compound AH where acidic protons are available. So at the end they will give hydrocarbon or alkane as a product. Look at one example. Grignard with water, it can abstract acidic proton, will give alkane. Even though with the carboxylic acid also it will give carboxylate salt of magnesium bromide and the alkane. Thank you so much.